Hello everyone. In today's lecture, we'll continue our journey with pulse modulation. In the previous lectures, we have learned about pulse modulation. We have seen that there are two types of pulse modulation, namely analog pulse modulation and digital pulse modulation. And we've also seen that both types require that the message is first sampled, and then the samples are used in the modulation process. And sampling, as you remember, provides discreteness in time domain. And we have talked about one type of analog pulse modulation, which was the pulse amplitude modulation, or PAM. And then we have talked about the quantization process, which results in discreteness in amplitude. And now that we have sampled signals, discrete in time, and then quantized, so we have discreteness in amplitude, now we can talk about digital pulse modulation. And in today's lecture, we'll talk about the pulse code modulation, which is the most basic form of digital pulse modulation. PCM, or pulse code modulation, is very famous, and it's one of the basic forms of digital pulse modulation. In PCM, a message is represented by a sequence of coded pulses, and we will talk about this kind of coding or coded pulses in a few minutes. And this is accomplished basically by representing the signal in discrete form in both time and amplitude. The basic operations performed in a PCM transmitter are simply the sampling, which provides discreteness in time, the quantization, which provides a discreteness in amplitude, and then the encoding process. And this operation, these three operations combined together, results in the so-called analog to digital conversion. And the device that performs this kind of operation is called an analog to digital converter, an ADC. And in some other courses, you will learn about the circuits used in the analog to digital conversion. This is a block diagram of the transmitter over here. We start with a continuous time message signal. First stage is to sample the signal, but as you remember, if the message or the signal is not strictly band limited, we have a problem. Therefore, we need to use an anti-aliasing filter. This low-pass filter acts as an anti-aliasing filter, which limits the bandwidth of this incoming message to a maximum of W. And now when we do the sampling, using the sampling theory, the sampling frequency Fs has to be larger than 2W. We will not be having aliasing distortion, thanks to this anti-aliasing filter. Then these samples are quantized using the quantizer we have discussed in the previous lecture, and there are two types, mid-rise and mid-tread, and these two quantizers are mainly uniform quantizers. And next, we will use the encoding process to translate these samples, which are now discrete in amplitude, into form of coded pulses, or the PCM data. Along the transmission path over here, we start using the so-called regenerative repeaters. If you remember from the previous lecture or the lecture before, we talked about the advantages of digital communication over analog communication. One of the advantages was the possibility of regenerating a clean copy of the message. And this basically can be understood as follows. If we have a message whose amplitudes are discrete, like this one, so the discreteness in amplitude simply means that we only have two amplitude, let's say for the simplest case to transmit. And let's say we have 0 and we have 5 volts. Now, having noise superimposed over the signal, this noise, since it's mainly additive, we can get rid of this noise simply because even though this voltage level is no longer a clean 0 volt and this voltage level is not a clean 5 volt, but we can still say, okay, if this is 4.5 or 4.7 or 5.1, we can still say this is originally 5 volts. And here, if it's not actually 0, it might be negative 0.5 or positive 1 volts or so. You still can say this is originally a 0. So we can get a clean copy of this message simply by having some sort of a decision device that will say, okay, any voltage above certain threshold will be considered as 5 volts, and any voltage level below this threshold will be considered as 0. This way we can get a clean copy of the message. Of course, this would be true unless we have large value of the noise, which will result in the voltage level 5 volts be getting below the threshold, or the voltage level 0 becoming larger than 0. In this case, than threshold. In this case, we get an error, and again we can use error control coding to overcome this phenomena. So in digital communication, we have the ability to regenerate a clean copy of the message to some extent. If the noise is limited to a certain range, we can get a clean copy of the message. So this happens along the transmission path until the receiver. And here in the receiver, the very first stage is again a regenerative circuit that will try to eliminate the effect of the noise. And then we perform decoding, which is the opposite operation of encoding. So basically translating the coded pulses we have into a PAM signal whose amplitude changes with the message. In other words, the samples over here at the output of the quantizer. And then we can use a reconstruction filter, a low-pass filter going from -W to W in a similar manner as we have discussed in the sampling process, and then we go back to our destination. So the low-pass filter prior to the sampling process is basically an anti-aliasing filter to limit the bandwidth of the message before sampling. And the basic operations in the receiver, as we have discussed, are basically regeneration of the impaired signal, decoding followed by reconstruction filter. And also along the transmission path, we have this kind of regeneration, the regenerative repeaters, along the path in order to overcome the effect of noise and interference. Additionally, by the end of this chapter, we will talk about the time division multiplexing, and when time division multiplexing is used, we need to have synchronization between the receiver and the transmitter, and we will see how we can achieve such synchronization. Okay, so let's take a closer look at the operations performed in a PCM transmitter. The first operation is a sampling process. The incoming message is sampled with a train of rectangular pulses, narrow enough to closely approximate an instantaneous sampling process. As you can remember, in instantaneous sampling, we multiply the message with a train of impulses. Impulses basically are pulses with narrow widths, ideally 0, going to infinity. But since we cannot generate this kind of pulses that has 0 widths and infinite amplitude, but we can generate pulses with narrow widths, not exactly 0, but narrow enough. And this is basically the sampling process. And again, we have to follow the sampling theory, which says that the sampling frequency Fs must be larger than twice the highest frequency component of the message, or W, the message bandwidth. So in order to ensure a perfect reconstruction of the message, Fs has to be larger than 2W. And of course, as we have said before, we need to use an anti-aliasing filter in case the message is not strictly band limited, which is the case for most messages. That's why we always need to use an anti-aliasing filter to exclude frequencies larger than W before we perform the sampling process. This way, the sampling process allows a continuously varying message to be uniquely represented by a limited number of samples per second. And by uniquely represented, we mean that we can recover the original message using these samples. The second operation performed in a PCM transmitter is a non-uniform quantization. So, the sampled version of the message is then quantized, thereby providing a new representation of the signal that is basically discrete in both time and amplitude. The quantization process may follow a uniform law as described in the previous section, where we have uniform steps, or the fixed or constant step size for all the range of amplitudes we have. But in certain applications, it's preferable to use a non-uniform quantizer, where we have a variable separation between the representation levels. If you remember, we had the so-called representation levels V1, V2, and V3 up to VL. These levels represent the discrete levels allowed at the output of the quantizer. In the uniform quantizer, we have constant or fixed separation between these representation levels, whereas in non-uniform quantizer, we have variable separation between representation levels. Why would we do something like this? Why would we need to use a non-uniform quantizer? For example, some signals, like the voice signal, might have a dynamic range of 1000 to 1. And a dynamic range basically is the ratio between the maximum amplitude to a minimum amplitude. So, consider a speech where we have sometimes peaks of loud talk and other times we have passages of weak talk. The dynamic range of amplitudes might be in the order of 1000 to 1. In order to understand this, let's take a look at this kind of signal we have over here. This is a typical voice signal or audio signal where at some instance we have weak passages with small amplitudes, and sometimes we have loud passages with large amplitude. If we use a quantizer, a uniform quantizer with a large step size, we would be using large step sizes like this one, fixed. This will simply mean we will not be able to distinguish these fine details. We will not be able to appropriately represent these small changes in amplitude. So, if we insist on using a uniform quantizer, we might need to reduce the step size in order to be able to represent these kinds of fine, small changes. We will end up with using smaller step size for the whole range of amplitude. This basically will result in a very, very large number of levels and consequently very, very large number of bits representing the signal. This is a problem. Additionally, in this range where we have large amplitudes, as a matter of fact, we do not need all these kind of levels, all these kind of details. We do not have these fine changes in the amplitude that need such large number of levels. But here, when the amplitudes are small, where we have these fine changes, we need small step size in order to be able to appropriately represent these small changes. So going back to our slide, so in some examples, in some signals like the voice signal, you might have a dynamic range of order 1000 to 1. And in this case, a non-uniform quantizer may be useful actually. In this case, we can change the step size. The step size can increase as the separation from the origin of the input-output amplitude characteristics is increased. This statement is kind of cryptic, but we understand it in the next few slides. In other words, simply put, the step size increases as the signal amplitude increases. So going back to the whiteboard, for smaller amplitudes we have small step size. As the amplitudes gets larger, we have larger step size. So we can use, or we can call it, a non-uniform quantizer. In other words, for larger amplitudes we use larger step size. For smaller amplitudes we use smaller step size. And here we can approximately achieve the so-called uniform percentage precision, which is basically a percentage or a ratio between the signal amplitude and the step size. Larger amplitudes, larger step size; smaller amplitudes, smaller step size, and in this case the ratio between the amplitudes and the step size is almost uniform across all the amplitude range. So, using a non-uniform quantizer, we have larger step sizes for the larger amplitudes and smaller step sizes for smaller amplitudes. So the large step size near the end of the quantizer characteristics, in other words when the amplitude is large, can take care of the possible large amplitudes in this case, which occur relatively infrequently. It doesn't happen a lot, this large amplitudes. So the small valued portions of the signal, the portions of the signal with small values, with fine details, which needs more protection in terms of being represented appropriately, are favored by using smaller step size, whereas larger step sizes are used for large valued portions of the signal, where large amplitudes with no fine details or not so much of fine details, we might use a larger step size. This is the basic idea behind a non-uniform quantizer. Okay, in this way we can achieve nearly a uniform percentage precision. Again, a percentage or a ratio, so the ratio between the amplitude range and the step size is almost uniform. Larger amplitudes, larger step size; smaller amplitudes, smaller step size. Therefore, using a non-uniform quantizer would require fewer steps or fewer number of levels, and hence fewer number of bits, as compared to the case of a uniform quantizer. Going back to the whiteboard over here, if we use a uniform quantizer with such small step size, we will need very large number of levels, very large number of bits to represent such a signal. But using a non-uniform quantizer with smaller step sizes for smaller amplitudes to capture this kind of fine details, with larger step size for larger amplitudes, we will end up using less number of levels and hence less number of bits to represent such a signal. This number of bits will require less bandwidth, less time for transmission, and so on. So the use of a non-uniform quantizer is equivalent to passing the message signal through a circuit that we call a compressor, and then applying this compressed signal to a uniform quantizer. So actually, the non-uniform quantizer is a circuit called compressor followed by a uniform quantizer. And we're gonna understand this in a few seconds in the next slide. So basically there are two kinds of compression laws that are used in practice. One used in North America that's called the mu law, and it's defined as follows. Absolute value of mu is equal to log 1 plus mu times the modulus of m over log 1 plus mu, where m is the input to the compressing circuit, the compressor circuit, and v is the output from the compressor circuit. Mu is just a constant. Let's move to our whiteboard over here. So we have a compressor circuit. The input is m, and the output from the compressing circuit is V, and this output is applied to a uniform quantizer, and hence these two combined together will result in the so-called non-uniform quantizer. So a non-uniform quantizer is simply a compressing circuit followed by a non-uniform quantizer. M is the input to the compressing circuit, V is the output from the compressing circuit. And please note that the log used over here is a natural logarithm, which is len in our terminology, or log to the base e. M and V are normalized input and output voltages, normalized with respect to the maximum. So whatever the maximum is, you normalized M to its maximum value, so you get a normalized signal M whose maximum is 1 right now. Same for V. V is a normalized signal, and mu is a positive constant. So M and V are respectively the normalized input and output voltages. About the log, if you know in MATLAB, for instance, in MATLAB, if you want the natural logarithm, which is log to the base e, it's simply called log. We used to call it in mathematics len. So it's kind of confusing, but our len, the natural logarithm we have learned about in mathematics, which is log to the base e, is in MATLAB it's called log. Whereas the log we are using in mathematics, which is log to the base 10, in MATLAB we call it log 10. So be careful when using this notation in MATLAB, and in some textbooks the notation log might refer to actually a len, which is a natural logarithm. Okay, so for convenience of presentation, the input to the quantizer and its output are both normalized as to occupy a dimensionless range of values from 0 to 1. Basically, M and V, the input and output, are normalized such that you have a range going from 0 to 1. So as you can see over here, this is mu low, this is the input M, this is the output V, and if mu is equal to 0, we get a straight line, which corresponds to a uniform quantizer. Whereas as mu increases, the curve starts to bend up like this. There's another compression law, it's called A law, and the A law, which is this one, is mainly used in Europe. The two laws are equivalent in a way, they perform the same functionality, but they are defined in different terms mathematically. But in order to understand how does this work and how does this compression law actually results in a non-uniform quantization, let's move to our whiteboard. So moving to our whiteboard over here, let's say we have a mu low curve over here, as you can see. And let's imagine that, of course, this is M, the input to the compression circuit, and this is V, the output from the compression circuit. And let's imagine that the input M is divided into uniform steps like this one. So now we have uniform steps for the input message. So let's see how this compression law will affect these steps. So the output in this case will be having this kind of range corresponding to this range of the input. So I'll call this range number 1. As you can see, it has been translated into a wider range of amplitudes. And this second range over here, it will be translated into a smaller range of amplitude compared to range 1. And if we move on to the third interval over here, using this law, we will see that it has been translated into a smaller range of amplitudes. So as you can see, the larger amplitudes are being compressed in a way. This is the fourth interval. So the larger amplitudes are being compressed in a way to a smaller amplitude in the out. So this, if we have a circuit following this kind of relation between input and output, the smaller amplitudes are kind of expanded or extended to a wider range of amplitude, and the larger amplitude are kind of compressed. That's why it's called a compression circuit. Now, if this kind of output, the compressed output, is applied to a uniform quantizer, so we have uniform steps, like this one, the ones in orange. Let me draw it in orange. So in this case, as you can see, the first range will have more levels than the second range, than the third, than the fourth range. So using a uniform quantizer for this compressed circuit will result in larger number of levels for the first range, which is basically the small amplitudes over here. So range 1 right now is getting larger number of levels, which means smaller step size. But range 2 of the compressed signal is getting fewer number of levels. So the range number 2 over here will get smaller number of levels, in other words, a bit larger step size. And this goes as well for the range 3 and 4. For instance, range 4 is getting only 2 levels in this representation, so the range of amplitudes here, 4, will only get 2 levels, which means larger and larger step size. So using this kind of compression followed by a uniform quantizer will result in more levels for smaller amplitudes, which means smaller step size, and less levels for larger amplitudes, which mean larger step size. And this is basically what a non-uniform quantizer would do. So going back to our slides over here, practical values of mu tend to be in the vicinity of 255 or so. And the case of non-uniform quantization corresponds to mu equal to 0. If you go back to the expression over here, if mu is equal to 0, you get log 1 over log 1, which is basically will give you 1, and the slope will be v modulus v equals modulus m. And in this case, as you can see, this is mu equal to 0. And of course, over here, you will have a uniform relation between input and output. So same number of levels appearing in the output will be identical to the ones appearing in the input. And in this case, we will be having a uniform quantizer. Another compression law that's used is basically the A law. It's used in Europe. It has a different definition. I will not go through it. It's basically, it looks like this for A equals 1, 2, up to 100. And in this case, a typical value of A would be in the vicinity of 100. And the case of a uniform quantization would correspond to the case where A is equal to 1. In the mu law, it's mu equal to 0. The mu law is mainly used in North America. It's basically used in the US, in Canada, and Japan, whereas the A law is used in Europe. The third step, or the third operation performed in a PCM transmitter, is the encoding process. In the encoding process, the output from the quantizer, be it a uniform or non-uniform, it's usually non-uniform quantizer, is transformed or translated into a form of coded pulses. So the processes of sampling and quantization has already transformed a continuous message into a signal that's both discrete in time and amplitude. The encoding process translates these discrete set of sampled values into a more appropriate form of signal, appropriate for transmission. And usually the binary code is used in this kind of operation. In a binary code, each symbol may be either of two distinct values, 1 or 0, which are known as the bits or the binary digits. In practice, the binary code is preferred over any other kind of code for two reasons. The first reason is that the binary code provides a maximum advantage over the effects of noise in a transmission medium obtained by using a binary code, because the binary symbols withstands a relatively high level of noise. What does it supposed to mean? Let's move to our whiteboard over here and assume that we have a binary signal where we have only two amplitudes, 0 and 1. And let's say that this signal is basically a voltage level 0 and the other voltage level is 5 volts, so 0 and 1. And let's assume that we have noise that's basically superimposed on this signal. As we have discussed before, we will have some sort of a threshold, usually in the middle between the two voltage level, usually at 2.5 in this case. And if the signal is below 2.5, we will assume it's 0. If it's above 2.5, we will assume it's a 1 or 5 volts. So in this case, if you think about it, what would be the maximum amount of noise allowed in this case, or what is the maximum amount of noise a binary signal can withstand? As you can see, it's basically 2.5 volts. If this 0 volt is affected by noise of amplitude up to 2.4 or so, we still can say it's originally 0. And if this 5 volt is affected by a noise or contaminated by a noise of amplitude minus 2.4 or so, we can still say it's originally 1. Okay, but if the noise, of course, is larger in amplitude, larger than 2.5, we will mistake a 0 for 1 and so on. Imagine that we are going to use another system, another coding system, and instead of a binary system, let's say a quaternary system. In a quaternary system, we'll have 4 levels. So, in the range from 0 to 5, we will have 4 levels instead of 2 levels. In this case, this is 1 level, this is 2, this is 3, and this is 4. And now we have 4 discrete levels in a quaternary system instead of 2 levels in a binary system. Now, what would be the maximum amount of noise this kind of signal can withstand? So, if this signal is affected by noise, now I need a threshold to compare. So, if this is these two levels are mainly separated by 5 by 3, so this delta is 5 volts over 3. So instead of dividing 5 by 1 in this case of binary signal, so the whole range here is 5. Now here is a range between two levels is 5 by 3. So the maximum amount of noise I can withstand would be basically depending on the threshold we have over here. So it's basically delta by 2, which is 5 over 6. So instead of being able to withstand a noise of 2.5 volts amplitude, we only would be able to withstand a noise of 5 over 6 volts, delta by 2. Otherwise, if the noise is larger than this value, I will mistake this symbol for this symbol, or this level for this level. So let's go back over here and read one more time. So the maximum advantage over the effect of noise in a transmission medium is obtained using a binary code, because a binary symbol withstands a relatively higher level of noise. If we have less number of discrete amplitudes, I would be able to distinguish between them easily. But if I have larger number of discrete amplitudes, the noise might make the distinguishing between them a bit more difficult. And the second reason why we usually choose binary code is that the binary code is easy to generate and regenerate, in other words, in a regenerative repeater. Okay, so let's assume a binary encoding with R bits per sample. That is, each sample is represented by a binary code word consisting of R bits. Having R bits means we can have 2 to the power R distinct numbers or distinct levels. If you remember, if we have 2 bits, we'll be having 4 levels, 0, 0, 0, 1, 1, 0, 1, 1. If we have 3 bits, we would have 2 to the power 3, which is 8 distinct levels, which are 0, 0, 0, 0, 0, 1, and so on. So if we have R bits per sample, if we are going to represent each sample by R bits, now we might be having 2 to the power R distinct numbers. So for example, if we have 8 bits per sample, this means that the quantizer we have is having 256 levels. So the number of levels in a quantizer is translated into bits. In general, the number of bits per sample is log to the base 2 of the number of quantizer level. If you have a quantizer level of 256 levels, the number of quantizer level is 256. Now log this number to the base 2 will give you 8, which is the number of bits required to represent every sample. And this relation implies that larger number of levels would require a larger number of bits, and hence larger file if you want to store it in your computer, or a larger transmission time and requirement for a larger bandwidth in case you want to transmit this kind of signal. That's why we use an uniform quantizer in the first place, in order to reduce the number of levels and hence reduce the number of bits. One question on the side: how would you calculate log to the base 2? Usually our calculators would be able to compute the log to the power 10 or log to the power e, which is a natural logarithm. In order to compute the log to the power 2, to the base 2, it simply goes like this. We have learned in mathematics that log a to the base e is equal to log a to the base c over log e to the base c. So we're simply saying here, if your calculator calculates the log to the base 10, so log a to the base e would be simply log a to the base 10 over log e to the base 10. In other words, if you want to compute log r to the base, log the number of levels, I will call it n, to the base 2, it's simply log n to the base 10 over log 2 to the base 10. Okay, and now we can get an estimate of the required bit rate. The bit rate measured in bits per second would be R times Fs. What's Fs? Fs is the sampling frequency or the sampling rate. In other words, the number of samples per second. So if we have 1,000 samples per second, and every sample would require R bits, R is the number of bits per sample, let's say 10 bits. So 1,000 samples per second times 10 bits per sample will give you 10,000 bits per second, 10 kilobits per second. And this bit rate in bits per second will give you an idea what kind of bandwidth you would need. If you remember from our discussion in the Fourier transform, the bit rate would be directly related to the bandwidth required. So now we can get an idea about the bitrate requirement and how it's related to the two operations we have been talking about. First, the sampling. So choosing Fs, larger Fs would mean we would be able to recover the message easily, but it would also translate into larger bitrate. So we want to find the minimum acceptable sampling frequency in order to be able to recover the message with the minimum bitrate. Same for the number of levels or number of bits per sample. Using a quantizer with large number of levels will result in having large number of bits per sample and hence having a larger bitrate. So we want in the quantization process to use a quantizer with the minimum number of levels that would be enough to represent the message without losing a lot. Okay, there are several ways of establishing a one-to-one correspondence between the representation level and the code word. The output of a quantizer is in the form of a representation level, V1, V2, V3 up to VK, if you go back up to VL, if you go back to the previous lecture. And now we have a binary code word, and a convenient method is to express the index of this representation level as a binary number. So if you are using level V1, you will just encode 1, so which is 0, 0, 1. If you have level number 3, you would encode it as 0, 1, 1, which is a binary representation of 3. So we are encoding the index of the representation level as a binary number. So if you have a level number 3, you would be using 0, 0, 1, 1, and so on. And this table would remind you of how to transform a decimal number into a binary number. I assume this is a straightforward operation for you guys. So now that we are done with the operations in the transmitter, we can move on to the regeneration along the transmission path. So along the transmission path, the most important feature of a PCM system lies in the ability to control the effect of distortion and noise, basically by using regenerative repeaters, by trying to regenerate or create a clean copy of the message. This capability is accomplished by reconstructing the PCM signal by means of regenerative repeaters, which are located sufficiently close enough along the transmission path. And located at sufficiently close spacing means that if you increase the distance between regenerative repeaters, the signal will fade out and the noise might be of significant effect on the signal, and you might not be able to get a clean copy of the signal, or you will be getting a copy with many errors. So you want to keep the distance between regenerative repeaters close enough in order to be able to get a clean copy of the message. The three basic functions performed by a regenerative repeaters are equalization, timing, and decision making, as you can see over here. This is a distorted PCM wave. First stage would be an equalizer, followed by a timing circuit, and then a decision-making device. Let's take a closer look at each block of these blocks. So an equalizer shapes the received pulses so as to compensate for the effects of the amplitude and phase distortions produced by the transmission characteristics of the channel. This simply means that if you go to our whiteboard over here, going through the channel, the PCM pulses will be kind of distorted. The frequency response of any channel is never flat. It's usually something like this. It's not flat. This is the frequency response of the channel, H of F. So if we transmit a PCM signal, let's say occupying this band of frequencies, as you can see, this portion will be saying a smaller gain, this part of the message will see a larger gain, and this will cause a distortion. That's why at the receiver we need a circuit that would have the inverse relation to this part of the channel response. We would be looking for an equalizer to inverse the effect of the channel, to reverse the effect. In other words, we will need a device would have this kind of response. A higher response over here with larger amplitude and a smaller response over there. This would be our equalizer. And we have discussed this concept in the previous lecture when we talked about the aperture effect, if you remember. So, the first step is the equalizer, which shapes the received pulses so as to compensate for the effect of the amplitude and phase distortion produced by the channel. The next block is a timing circuit, which is basically we're trying to extract a clock or square pulses from the output from the equalizer. So the timing circuit provides a periodic pulse train derived from the received pulses. And this is done in order to perform sampling one more time, to renew the sampling, to perform sampling one more time of the equalized pulses in order to obtain a clean copy or to obtain clean copy of the signal by sampling the received signal at instance where the signal to noise ratio is maximum. And in order to achieve this maximum signal to noise ratio, we will be using a matched filter or so, which you will learn about in a different course. These extracted samples are then compared to a threshold. If it's larger than certain threshold, we will decide it's a 1. If it's less than the threshold, it will be decided to be a 0. And this is the third block, which is a decision-making device. So, in each bit interval, a decision is made whether the received symbol is 1 or 0 based on a threshold. If the received signal exceeds a threshold, we will say it's a 1. If it's less than a threshold, it will be 0. So going back to our slides over here, it's similar to this concept we have been talking about. We have a threshold. If the received signal is larger than a threshold, it's logic 1. If it's less than a threshold, it's logic 0. So in this way, the accumulation of distortion and noise throughout the communication channel is removed by generating a clean copy of the message every time, provided that disturbances is not too large, the noise is not too large that it would cause an error in the decision-making process. Again, if the noise is large enough, as we have seen over here, if the noise is large enough, I might decide that this level is 0 even though it was a logic 1. Same over here, if the noise is too large, I can decide that this symbol was 1 even though it was 0. So errors might happen. So, and in this case, of course, as we have discussed previously multiple times, we can use a so-called error control coding. So in practice, the regenerated signal might be different from the original signals for two main reasons. So in a regenerative repeaters, things are not ideal. We have many sources of error and noise. The first source is basically the unavoidable presence of channel noise and interference, which might cause the regenerative repeater to make wrong decisions, which will result in errors in the received bits. And in this case, we can use the error control coding to detect some of these errors and correct some of these errors. The second source of error is called the jitter. It's kind of a new term for us. Let's try to see what does this word mean. If the spacing between the received pulses deviate from its original value, so we have received samples. If the position of these samples or pulses deviates from its original position, we have a phenomenon that's called jitter. And this jitter will result in a sort of distortion. In order to understand this concept of jitter, let's go back to our whiteboard over here and try to understand what does this mean. So the jitter basically means that the samples are arriving at wrong timing. So basically, if we have, let's say, a sinusoidal signal like this one. So it's first sampled. So we have a sample over here, and let's say a sample over here, and sample here, and so on. So if these received samples are arriving at the wrong time instant, so if the spacing between the received samples or received pulses deviates from its original position. So let's say this sample arrived as is, but this one has arrived a bit later than its position. So if this sample has drifted like this, it was received later than it should have been. And let's say this sample are received as is in the correct timing, and let's assume that this sample has been received a bit earlier than it should be. Then if we try to reconstruct the original signal, you might get a distorted signal like this, the one in red. It's kind of distorted compared to the original signal because of the shifted samples, or the samples arriving at the wrong time instant. This phenomenon is called jitter, and this will also cause distortion in the received signal. Finally, at the receiver, the operations performed at the receiver will start with decoding and expanding. The first operation is to regenerate the received pulses in the same manner as we have done in the regenerative repeaters, by creating a clean copy of the message. These clean pulses are grouped together and into a code word, and then it's kind of decoded into a quantized PAM signal. So we have received a sequence of ones and zeros, which will be grouped into a digital word, binary word, and this binary word would be used or decoded in order to regenerate the original sample valued signal, the PAM signal. That is to generate a pulse h of t whose amplitude is a decimal number equivalent to the binary number received. In other words, we are doing the opposite to what we have done in the transmitter. In the transmitter, we have this decimal number representing the representation level. We have transformed it into a binary number. Now at the receiver, this is the received binary number. We will group the received bits into code words and then translate these code words back into indices for the representation levels. Now the sequence of decoded samples represent an estimate of the sequence of the compressed samples produced by the quantizer in the transmitter. Remember that these representation levels are kind of compressed because we have used a compressing circuit in order to achieve the non-uniform quantization effect. Now these samples represent the compressed samples. And here is where we have a question. Why we are saying an estimate? Because there are many sources of error in this case. We are saying an estimate of the compressed samples because we have errors. We have many sources of errors, including the quantization error in the transmitter, the noise and interference and jitter along the transmission path. So, in order to restore the sequence of the decoded samples to their correct relative levels, in other words, instead of being compressed, we need to decompress them. We need to use a circuit that's called an expander that would have the inverse characteristics or a complementary characteristic to the compressor. In other words, if the compressor we had was a mu law, for instance, with the curve that we have seen, now we need an expander circuit of an opposite characteristic, something like this. This would be an expander circuit. And now, as you can see, if we have uniform levels over here, this range of amplitude would be translated into a smaller or compressed range of amplitudes, whereas the larger amplitudes will be translated into a wider range of amplitude, hence it was kind of expanded. So this is basically the opposite of what had happened in the compression law. If you go back to the compression law we have seen, here this is a compression circuit. The larger amplitude are kind of compressed into smaller ranges of amplitude, whereas here in the expanding circuit, the larger amplitudes are being expanded into a larger amplitude range. So in order to restore the sequence of decoded samples, we need to use a system that has a complementary characteristics to the compressor. It's called an expander. And the combination of compression and expansion is referred to as companding. A compander or a companding process, it basically represents the compression happening at the transmitter and the expanding happening at the receiver. The next step in the receiver is the reconstruction. by basically using a reconstruction low-pass filter, as we have discussed in the sampling part of this chapter, where we have a low-pass filter with a cutoff frequency W equal to the message bandwidth. This reconstruction filter will eliminate the periodicity in the frequency domain and hence recovering or reconstructing the original message. And if we have the aperture effect, we might need to use an equalizer, as we have discussed previously. And here we are talking about reconstruction of an estimate of the message rather than an exact reconstruction. Again, we do not have exact reconstruction, we have an estimation of the original message. Again, due to the many sources of error, the quantization error, noise, interference, jitter as a channel, and many more effects, many more channel impairments that would affect the received signal. So it's an estimation rather than exact reconstruction. One last comment over here, the word modulation in PCM is kind of misleading. It's a misnomer, it's kind of inaccurate. Because as we're going to learn in the Digital Com1 course, modulation is a different concept and it's not exactly what's happening here in PCM. In reality, what's happening here in PCM is the so-called source encoding strategy. Source encoding. It's basically, we have an analog signal emitted by a source, and this analog signal is converted into a digital form using PCM. PCM is not kind of modulation, it's not a modulation, because we do not have a carrier whose characteristics is changed in accordance with the message. But if you think about it, in PCM we have an analog signal that's transformed into a digital binary form, ones and zeros, so it's called source encoding. We try to encode the message coming out from a source into a digital form. And this will be it for today's lecture. In the next lecture we will talk about the line codes and the time division multiplexing.